Good morning, everyone. Hello. Some of you I've already seen once this morning in the tutorial. It's nice to see you again. The rest of you, welcome. So, a few little pieces of housekeeping, and then I'm going to talk about this week. So, firstly, I'm going to put this bit of canvas on the screen. Couple of things. Firstly, what's due on Sunday? Now, I want to talk about special consideration. Some of you will need it. Class of 170. Plenty of you will have had something come up which will make it difficult for you to complete your assignment in time. I can't do anything myself. It's got to go through the Special Considerations Office. This assignment is also eligible for simple extensions, so that is fine as well. The one catch about this is that my markers are going to start marking basically on the deadline, which means that if yours comes in after they finish their marking, they probably won't see it until a sweep at. My promise to you is that if you submit your assignment on time, you'll get your grade back within 2 weeks. But if you don't submit it on time, it's possible it may not get picked up until after that, although it's unlikely. So just be aware that if you submit it late, we don't guarantee that you'll get it back. Like, you all got it. A second thing, so as you know, in week 7 there's a mid-semester exam, and I thought now is the time to show you what that exam will look like. Not the questions, but everything else. Just so you know, you have an idea, because as you know, you can't bring anything in, I want to show you particularly the last 3 pages, which are the formula sheet. So there'll be a front page, unexciting. There'll be a question 1, and you will get 2 pages to write it in. A question 2, 2 pages, question 3, 2 pages, question 4, 2 pages. Each of the 4 questions is designed to take about 10 minutes if you know what you're doing. If you don't know what you're doing, then you might run into some time issues. There are 3 more pages. The first is a whole bunch of vector calculus formulas that I don't want you to have to remember, including the 3 big vector calculus theorems. The second is a bunch of multivariable calculus formulas that I don't necessarily want you to remember, including this one here, the trace determinant form of a matrix eigenvalue, which you should know, but maybe you don't. So it's there, and your standard coordinate Jacobians. And the third is a table of integrals that you may or may not need, but I put on every exam just in case. So this is just so you can familiarize yourself with this now and know what you don't have to commit to memory. But of course, knowing these things in your head makes it a little easier to see what is important and where you might want to use it. So my recommendation is not to rely on this, but to treat this as a helper. You know, I happen to know in my head that Stokes' theorem relates a surface integral to the line integral along its boundary. You may not remember the exact formula, but you know that's a thing, and therefore this may be useful. So just bear that in mind. That is enough about that. I just wanted to cover those things. Now we're going to get into this week. So I gave you a bit of a heads up that there's a lot of content this week. My plan is basically to use the first half hour of the seminar as the end of the lectures. So there's probably about 3.5 hours of lectures this week. So when you come to the seminar, when you come on Thursday to whatever it is you come to, then you should expect a little more lecturing to happen before we do any fun computer stuff. Okay, so quick recap. The thing you learned about last week with me was the line integrals, which is sort of a new idea. And a line integral looks like this. And it has 2 ingredients. The first ingredient is some curve parameterized by t. So some curve which moves, in our case, from t equals a to t equals b. And it is parameterized by t. And the second ingredient, so our first ingredient was a curve, parameterized. Which we are going to call sigma of t. Our second ingredient is a vector field, which just lives in the background and relates every point in our domain with some output in Rn. This is a bit of a messy field, but it does the job. So some background vector field. Vector field, which we're going to call F. And of course, we will be evaluating this vector field on our curve T, so we'll be parameterizing it in that way, which is really F of sigma of T. So we've got a background vector field and we've got a line, and the question is, what does this give us? The line integral is the integral of the field's projection onto the direction of the curve. So the direction of the curve is, of course, the tangent vector at a point. So I'm just going to get rid of this bit of field so I can write this. That is my derivative in the curve direction, which is to say the direction of the tangent vector. So because fields have directionality, integrals need a little bit more information, which is why we have these curves, because we want to work out how much of the curve is, how much of the field is acting in the direction of the curve, and that is why what a line integral is by definition. Okay, and I left you with a question. So if we change the vector field F, it's clear that the result changes. And the question I left you with is, what about if we change the curve parameterization? And I was a little bit cheaty here. We actually want to be a little bit more careful about what we mean by a curve, because we have essentially interchangeably used two different definitions of curve and treated them as the same thing. By and large, this is not a problem, but we're just going to be a bit specific here and say, okay, what is a geometric curve? A geometric curve, the kind of curve you probably learned about in first year, is a 1D set of points which might live in Rn. So you have some Rn and you've got some one-dimensional set of points weaving its way through. But that's not quite what we did on the last page. We defined our curve in terms of some vector, some map from T in R1 to sigma, which is an element of Rn. So a parametric curve is a map sigma from an interval. Remember, when we say interval, we mean in R1 to a set of points and these are slightly different things. The most significant difference between these two things is this one will have a notion of direction and this one will not. That's a little point which is relevant to this question about parameterization. So, if I take my two maps here, so my first map maps the interval 0, 1 into R squared, such that it's T and 1 minus 2. And my second map maps the interval 0, pi, different interval, into R squared, sine squared T and cos squared T. And if I draw those out, then my first map starts at 0, 1, and it moves down here, and it ends at 1, 0, and the interval moves this way, underneath right. So this is sigma 1 of T. But if I look at sigma 2 of T, sigma 2 of T, sorry, this should be 1 minus, no, it's right. Sigma 2 of T starts at 0, 1, and as I get up to pi, moves to 1, 0. So different values of T, but we also get sigma 2 of T. So these are, move this out of the way, these are the same geometric curve. They trace out the same set of points, but they are different parametric curves because it's a different map. So when I really say I want to know about two different parameterizations, I'm saying I care about the same geometric, but different parametric curves that trace out the same geometric curve. And let's, for now, say they trace it out in the same direction. Okay. So we're just being a little careful here because we can't really talk about the question without refining our terms a little bit. So how does changing the parameterization alter the integral? So I have some integral from t1 to t2 in terms of some map. So this is just a line integral from before, nothing new here. F is a vector field described on some domain, which is a subset of Rn. And our map goes from an interval, t1, t2, to d. And we're going to say that it's a parameterized curve, and to make our life just a little bit easier, although we're also going to relax this later, we're going to say that it's a differentiable curve. Well, we have a theorem, and we're going to prove it. And our theorem is that the line integral of a vector field f along a curve defined by sigma is independent of the parameterization of sigma. So, as long as I follow my curve, and it will turn out as long as I follow it in the same direction, then it doesn't matter at all how I parameterize it. It doesn't matter if I parameterize my curve using this or using this. It will give me the same result. And we are going to show that, because you shouldn't just believe me when I say things. Time for a theorem. Okay, so we're going to prove this. We're going to reparameterize the curve, and we're just going to show that the integrals are equal. It's a very straightforward, direct way of proving, no tricks. So we're going to define some stuff. Let g of u be a one-to-one function. And we want to keep things one-to-one, makes our life easy. And t equals g of u. So what do I mean by that? I mean that let g of u1 equal t1 and g of u2 equal t2. So g is 1-to-1 and t is equal to g of u. So t is my original parameterization and u is my new parameterization. And I want to show that integrating my parameterized curve over t gives me the same result as integrating it over u. Okay, and to do that, we do some calculus, which is probably good. We're going to start with our integral, and we're just going to follow all of these equal signs down until we get to the bottom. So, time to shake off the dust a bit. Okay. So what we want to do is write in terms of u. We need to change variables. And the good news is, this is a 1D integral. We don't even have to pull out the Jacobian. This is a very direct, very straightforward change of variables that you've all been doing since you were 6 years old. So, we integrate. I'm not going to change the bounds yet. I'm going to leave this as t1 and t2. But I'm going to write this as f of sigma of t, but t is g of u. So what I've done is I've replaced sigma of t with sigma of g of u, which is just a function of u. Dot product doesn't change. Sigma dash also becomes g of u. So here, this t becomes g of u. And finally, I haven't changed the dt yet, but I will. So I haven't changed the bounds and I haven't changed the differential. I've just got u into my integrand. So don't forget that this thing here means d sigma dg. And we're going to have to make a change of this differential. So we're going to say, well, dt, I'm going to want an integral with respect to u, so it'll be dt du. But we know dt du because t is equal to g of u, So this is dg du. Right. So far, so good. Let's keep going and let's make these changes. So now I'm going to change my bounds to be from u1 to u2. I've made this change here. This is now in the form I want it to be in, so I'm not going to touch it lest I break it. But I am going to take a closer look at this. I'm going to write this as d sigma dg. And then I'm going to write my differential as dg du. So this was my dt. Okay, so my dt has changed to dg du, and I already had a d sigma dg, so this is a bit convenient. Probably I'll be able to replace this with dg du, which is exactly what I'm going to do. So we're tracking the algebra, basically. This proof is an exercise in keeping tabs on algebra. But what we want to do, be a bit careful about what this means. So I'm going to define a new curve. Let alpha of u be equal to sigma of g of u. So this is the same curve, it's just parameterized in a different way. So when I want to write this and forget about whatever g is, I'm just going to absorb g into my map. So now alpha is a map directly on u, whereas sigma is a map on t. By absorbing the g functional dependence into the alpha, I'm now writing my curve directly as a function of u. And just using the chain rule, single variable, this is going to be sigma dash of g of u, g dash of u. We don't need this immediately, but we are going to need it in about a minute. Okay, so what I'm going to do is I'm going to write this in a form that makes it more amenable to this transformation by saying this is the integral from u1 to u2. F happily does not change, will continue not to change. But this is now, alright, sigma dash of g dg du is g dashed of u du. But, running out of colours, we've replicated exactly this. We already have this. So if I put those pieces together, I get the integral from u1 to u2, f of alpha of u, dotted with alpha dashed of u, du, which is nothing more than the line integral in terms of u. So these two integrals are exactly the same. We haven't made a change, we've just thrown an intermediate map between u and t, and that hasn't actually changed anything. It's changed the way we write our curve, but this is pointing to the same set of points. It's pointing to the same geometric curve with the same orientation. So that lets us show that the integral from t1 to t2 of f of sigma of t, dotted with sigma dash of t, which is a bit of a wordy thing to write. Maybe we'll find a way to shorten that in a few slides. u1 to u2 of f of alpha of u dotted with alpha dashed of u du. Great. So as long as I can find this suitable one-to-one map between u and t, and we really do want this to be one-to-one, then the integral is exactly the same. And I didn't specify my reparameterization. I just kind of let the ball roll and fall where it may, which means that it doesn't matter which one we pick, we're going to get the same result out. It does not matter how you parameterize the curve, which is good. It would be very strange if it did. So, that was the proof. Oh, we did a proof. We get to draw a box. All right, what does that mean? Well, firstly, the parameterization has to be one-to-one. If it's not one-to-one, the proof we did doesn't work. Some of the things that we defined can't actually uniquely be defined. The second thing is it can't change the direction of the line integral. Remember, integrals have a direction. So it's not so much that the parameterization was a problem, it's the fact that the integral direction changes if we're not careful. So say, as an example, I want to integrate around the circle that I so perfectly drew. Well, the natural parameterization, one might say the obvious parameterization, is to say I want to map from 0 to 2 pi to r squared. Well, fairly obvious parameterization here. Cos of t, sine of t. Probably you can start anywhere on that circle you want, given that an integral is a sum, and in fact that is the case for a closed curve like this. But we will pick this one. But maybe I want it to be a bit difficult. Maybe I'm like, no, I'm clever. I know that changing the parameters doesn't matter. So maybe I think I'm being smart, and I try cos of 2t, sine of 2t. But I have a bit of a problem here, because this doesn't work. This doesn't work. If I take my first parameterization, I go around the circle and wind up where I started. But if I take my second parameterization, if I go from 0 to 2 pi, I go around my circle, and I go around my circle again, and I end up back where I started. This is not one-to-one. There is not a one-to-one map from the green to the red, because there are 2 points in the red that map to every point in the green. So this is not a one-to-one map, and you can see immediately how it's going to fail. It's going to trace out the integral twice. So that's the sort of obvious reason why a map that's not one-to-one fails. They can fail in more subtle ways, but this is a nice example. Do you have a question before I do the next one?
I know.
Okay, cool, good. Another terrible idea would be to say, well, I only really care about geometric curve, so I'm going to make my map cos of t minus sine of t. Now, this is a one-to-one map. It absolutely traces out each point once. It also maps the starting point to the starting point and the end point to the end point. However, it goes the wrong way, so it changes the orientation of the integral. We can't have that. So, sigma 1 and sigma 2 trace out the same circle, but it is not one-to-one. Sigma 2 passes through each point twice, and therefore the integral will not be the same. Sigma 3 absolutely maps out the same circle, the same geometric curve, but the path is reversed, which means the integral changes orientation. The orientation of line integrals is very important. We're going to come back to that later on. In general, we refer to curves that go counterclockwise as being positively oriented, and curves that go clockwise as being negatively oriented. There's nothing special about that choice. It was just at some point mathematicians had to sit down and pick one. So they did, and we're stuck with it. That makes sense. It goes the way the angle increases. So positively oriented, negatively oriented. Alright, take 30 seconds. You've done really well. Anyone here come from the stats quiz? Alright, 10 more seconds. 5, 4, 3, 2, 1. Nothing you say is important. Okay, so now you all listen to me. No, it's fine. This is good. So let's talk about C being a geometric curve from A to B. So A, B, and C are 3 points in some domain D, where D is the domain of a vector field F. What we're going to do is write this in a nice little way. We're going to write this as the integral along C. So C is a curve from A to B. We say the integral along C of f of r dr is equal to the integral from t1 to t2 of f of sigma of t sigma dash of t dt. Now, have I cheated here? Is this notation fair? Because this is the notation for a line integral that we've seen before. But now I'm saying this is a valid way of doing it. What happens to sigma? Do I need it? Can someone tell me why it's totally okay that I haven't specified sigma at all? Hand up. Actually, tell your friend. Alright, does anyone, now that you've had a chance to put your heads together, want to volunteer an answer? Does anyone think their friend said something sensible? I'm not going to cold call you, this is just judgy. Alright, what's the thing we just learned? What did we learn doesn't matter? Parameterization. So, does the specific parameterization matter at all? Not really. So sigma is in fact any parameterization of the curve such that it starts at A and ends at B and goes through each point of C once. And as long as you parameterize that way, then you're in business. So in fact, when you calculate these things, you typically have to come up with a parameterization, but the parameterization is just a calculation tool. It's not actually inherent to the definition of a line integral. And that's a really important takeaway because you will much more frequently see it written this way. Where the author says, you know what, you're smart, you took Math 2921, you can come up with a parameterization. And you can, because you're smart and you took Math 2921. So we can now take this and think about things more generally. What if I have two curves in space, C1 and C2? Well, in fact, I know that I don't have to come up with a single parameterization that takes me all the way there. And in fact, that means that this point here, where it's not differentiable, might not be a problem at all. So let's think about concatenation. We can use this to think about curves that aren't differentiable everywhere, which is exactly a situation I briefly alluded to. And in fact, this is true of a lot of line integrals, and may certainly be true of at least one line integral you need in an assessment context this semester. We think about two curves, C1 and C2. C1 parameterizes C just between T1 and T2, and sigma 2 parameterizes C2 just between T2 and T3. So the question is, can we join them together? Well, of course we can, because we can add integrals. It is totally reasonable to say that the integral from C1, f of r, dr, plus the integral from C2, f of r, dr. And this is a valid way to talk about an integral along this curve. And each of these two curves individually can be parameterized by a completely differentiable parameterization. So as long as we have a finite number of non-differentiable points, then we can keep breaking up our integrals this way and still come up with a valid definition of the line integral. So now I can write T1, T2 of f of sigma 1 of t dotted with sigma 1 of t dt plus the second integral, which goes from T2 to T3 of my field sigma 2 of t dotted with sigma 2 of t dt. And these two things are both smooth. So if I say sigma 3 is some curve that maps T1 to T3, and I'm going to say that in fact it parameterizes T1 to T2 and then T2 to T3, then sigma 3 will not be completely differentiable. However, the derivative is well defined on every point except T2. So I'm saying there is some sigma 3 that goes like this, and then the parameterization takes an abrupt left turn. In that case, my sigma 3 is completely smooth and differentiable except that point. So it's the only point which has an issue. But because we know that the parameterization doesn't matter and we're smooth everywhere else, we can break it up like this. And when you break up integrals that meet at a single point, you can ignore it, as you learned when you did these nasty integrals in first year. Technical reason you can ignore it, you can still construct the Riemann integral partition without any problems at all. You could tease that out into the full derivation, but basically, like, the Riemann integral is still valid as long as you have a finite number of jump discontinuities, which is exactly what you have in this differential. So in fact, I'm going to just add this at the bottom with finite jump discontinuities. And it's sigma dash. If I don't write it, someone will ask. And that's good. You should poke at the edges of that. Alright. So we've done precisely this. We're letting sigma 3 dash be sigma 1 dash to t if t is between t1 and t2. So along this line, sigma 3 is equal to sigma 1. And sigma 2 dash to t if t is between t2 and t3. So if we're going up here, then sigma 3 is equal to sigma 2. Makes sense. In that case, we can take our T1 to T3, f dashed of sigma 3 of t, dotted with sigma 3 dash of t, dt, and because this can be broken up at every point where there is a jump discontinuity in sigma dashed, we are completely free to write this as the integral from t1 to t2 of f of sigma 1 of t, sigma 1 dash of t, plus the integral from t2 to t3 of the other one. All of this is basically just saying integrals work when there's a finite number of jump discontinuities, but, you know, it tells us something quite important. If we define C1 plus C2 to be the geometric curve that is the image of sigma 3, which is what we mean when we add curves together like this, then it is reasonable to say that the integral of C over C1 plus C2 of f of r dotted with dr is equal to the integral of C1 f of r dotted with dr plus the integral C2 f of r dotted with dr, which is a very long and involved way to show that curve concatenation of line integrals is a completely valid thing to do. But we like this because a great many curves that we care about are not differentiable everywhere, and if our construction is valid for more than that, we should show it and then just trust it forever. Okay, so that was proofy. We didn't prove facts about the Riemann integral, but you did all of that last year, so territory. A curve is defined as piecewise smooth. This is terminology we will use later on in this subject without any further definition. A curve is piecewise smooth if it is the union of a finite number of smooth curves, where the end point of one is the starting point of the next one. So a piecewise smooth curve might look like this. This is C1, this is C2, this is C3. Between these points, they are all smooth, and at those points, they are continuous. So as long as it's continuous at joins and smooth everywhere else, then you have something that is piecewise continuous. Basically, integral calculus works nicely on piecewise smooth things. So this is a good definition to have in our back pocket, because chances are if you have some integral theorem you want to test, this is what it's good for, and anything more strict than this, it can't do. So this is kind of the natural limitation of the Riemann integral. Everything we did about the previous result, which was proven for one concatenation, is proved for piecewise continuous. Doesn't matter how many concatenations we have. We can define. So I'm using a word here. I'm using define. We're defining the negative of a curve. So the negative of a curve is the same curve, but in the opposite direction. This is a definition. It doesn't follow from any of the definitions we've stated so far. This is a new definition. We're defining minus c to be c, but with the reverse orientation. When you talk about curves, you should mention their direction, and if two curves are pointing in opposite ways, then we can call that minus c, and it's understood what we're talking about. And conveniently, this does follow from the math. The integral from minus c of f of r dr is equal to minus the integral of c. You might say, Chris, that's absolutely obvious, and it is, but you've got to show it. I mean, I didn't, but you can show it by reversing the parameterization. This is a fact that we took for granted in one-variable integrals, things you take for granted in one-variable integrals don't always port 100% to line integrals. So when there is something that does, just completely without any changes, map through, we've got to at least state that. You probably all assumed this was true, but now you know it's true. All right.
Does it also work if you just plug in the t's negative from T2 to T1?
Yes, once you have formulated it correctly. So what you're doing there is you are essentially reversing the map. So the best way to think of that is rather than flipping the t's, because remember, it's talking about a slightly different operation, what happens if we reverse the interval in the map. So we're actually changing sigma, which has the effect of changing the t's. You're not wrong. But there's a more fundamental piece in the engine room. Okay. Well, that's a lot of talk. Let's talk about some notation and then do an example. So some notational stuff. So we have some field, and I'm going to say my field f depends on f1, f2, f3, all the way up to fn, where they depend on my x's. This is a really common setup to see, is the vector field depends on intermediate bits and pieces. We have our curve, and we're defining a parameterization here, although, as you can imagine, it's going to vanish from this discussion pretty quickly. So sigma is our parameterized curve. So f depends on some function of our parameterized curve. And this integral here, if we expand all of this stuff out, is f1. This is supposed to be an equals f1 of x1 to xn, f2 of x1 to xn, dot dot dot, fn of x1 to xn. So things are getting a bit big here. And here we have sigma dash, so that's dx1 dt, all the way through to dxn dt. So all I've done here is expanded this out, nothing tricky. But this is just a dot product. So I can write that dot product out, t1 to t2, and I get f1 dx1 dt plus f2 dx2 dt plus dot 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 plus fn dxn dt, all dt. Now if I break this into n different integrals, each one of these has a different integration by substitution going. So the way we write that, and we're going to define some notation. So when I write this, what I mean is this is a definition. Is we write that as t1 to t2
f1 dx1 plus f2 dx2 plus dot 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 plus fn dxn. And this thing here is a really important quantity. So this is known as a differential form. It's essentially the differential form of an integral. What this is kind of telling you is what your integral does, but it's a point form. So rather than being a non-local operation, which it is on an integral, this is purely a local operation, which is kind of telling you what the integral would be at t. It doesn't matter if those subtleties are a little bit much, but you will see this, and we will use this form, and you should know that this form means this, or this if you like. If you see this in the literature, it's called a differential one form, or a differential form, or a one form, if people know you're talking about differential forms. The idea being this encodes what an integral should do for the vector field. So vector fields have associated one forms. There are higher forms which relate to higher integrals. We're not doing multiple integral forms, so you don't have to worry too much about it. But you should recognize if you see this written down what it means. Probably the take home on this slide. Alright, an example. C is a triangle. It has vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and because we like our curves to be oriented, it is in that order. And I want to evaluate up this one form. We know that it doesn't matter how we parameterize this curve. I went to great lengths to convince you that this was true. But if we want to actually calculate an integral, we have to roll our eyes, suck it up, and come up with a parameterization. So that is what we're going to do. I'm going to parameterize the first curve, C1, that goes from 1, 0, 0 to 0, 0, 1 to 0, 1, 0, as sigma 1 of t is 1 minus t, t, 0, where sigma dash of t is equal to minus 1, 1, 0, and t is 0, 1. So the idea here is, as t is at 0, I'm at 1, 0, 0, because this thing is 1, and this thing is 0, but as t goes up to 1, this follows a straight line that takes me to 0, 1, 0. So check, everything works. We're going to construct the other two in the same way. So sigma 2, which goes from 0, so x is always 0, y goes from 1 to 0, and z goes from 0 to 1. So sigma 2 dash of t is 0 minus 1, 1, and t goes from 0 to 1. And sigma 3 of t starts at z equals 1 and finishes at x equals 1, and y is always 0. So sigma 3 dash of t is equal to 1, 0, minus 1, with t following 0 to 1. You could come up with other parameterizations. They would always work. How do I find the simplest parameterization? With your heart. Lines should probably look like lines. Circles should probably look like circles. And anything else, you're on your own. Have fun with it. Knock yourself out. There's a lot of ways to parameterize. Some easy to integrate, some hard. Parameterization of curves is a sticking point for a lot of students, and I'm practicing. Okay, so we'll do the integral now to show you how that happens in a few lines. So, minus y dx plus x dy plus 2 dz. Sigma 1 of t is 1 minus t, t0, so this was 1, minus 1, 1, 0. Dx is equal to dx dt. Dt is equal to minus 1 dt. Dz is equal to 0 dt. Dy is equal to dy dt. Dt, which is equal to 1 dt. So this thing is equal to the integral, t goes from 0 to 1, minus y. So minus y is minus t. So this is my minus y. Then I get my dt, my dx, which is minus 1 dt. So this is my dx. Plus my x, which is 1 minus t. is x. And my dy is 1 dt plus the 0 from the dz. So, minus t comes from this. 1 minus t comes from that. Minus 1 comes from this, as does the 1. And the dx and the dy come from this. So you put all the pieces together, and once the setup is done, the integral is normally, if I haven't been mean to you, and I'm not a mean person, relatively simple to integrate. Integral from 0 to 1 dt, which is 1. We can do the others the same way. I'm going to do those because we have 5 minutes left, but I'm not going to dwell too much on it. So sigma dashed minus 1, 1. dy is equal to, well now dy dt is equal to dt is equal to minus 1 dt. dz is equal to dz dt, which is equal to 1 dt, and dx is equal to 0 dt. So you put the pieces together, and I'm not going to color coordinate at this time because you all get the idea. 0 to 1, 0 dt plus 0 minus 1 dt plus 2 sorry. Yes, 2, because 2 is 2. 1 dt, which is the integral from 0 to 1 of 2 dt, which is 2. Okay, you can do the third one, and I will fill this in, but I don't want you to sit here and watch the same thing 3 times. So I'm going to say this integral, and you should convince yourself that this is the case, becomes the integral from 0 to 1 of minus 2 dt, which is minus 2. So if I put everything together, again, the integral from c minus 1 dx plus x dy plus 2 dz is equal to c1 plus the integral c2 of the same plus the integral c3 the same which, since we did our algebra correctly, because we're ever so clever, 1 plus 2 minus 2 equals 1. So the answer is 1. You should convince yourself that a different parameterization of these curves gives you the same answer. Now, before we wrap up, I want to say something about this and ask you a question about it. Which is, remember how I said earlier today that stuff from one variable calculus doesn't always photocopy nicely into line integrals? Well, the question we're going to ask tomorrow is, does the fundamental theorem of calculus copy straight into line integrals? Intuitively, it's not obvious that that's the case. Sure, the parameterization doesn't matter, but what about the path? The endpoints don't know about the path. Is it still possible to write down a fundamental theorem of calculus if the path matters? Or does the path matter? The question I want you to think about tomorrow is, does the path matter? And if the path doesn't matter versus if it does, what does that mean? Alright, I'll see you all tomorrow.
after we
The first time individual skills I 4 minutes before that.
yeah, I think we can stop them outside and
Yes.
yeah.
Yeah.
I'm doing the quiz right now. Go outside.
Doing the quiz
Quiz right now.
for step 2
Yeah.
can you move out for that first and then yeah, we're gonna put on the yeah. Thank you. So I'm really sorry. So we have oh yeah, so
So currently, since this small, we cannot do the one seat apart, right?
how many students are there in total? 120.
We cannot do the one seat apart.
We have how many rows in there? 9. Yeah. 9.
Just alternate.
Yeah, we can put that up. Yeah. So every row gonna have students, but yes. I could do this one and then I'll just put like
Yes. Checker.
oh yeah, I should check this. Sometimes it's a bit should be when there's a class before the class, like before the
I think they ended like 5 minutes.
yeah. Else it's gonna be even. Last time it was like even late. And doing class later, so I was like, oh. So I'm gonna just put one over here. And then oh, the whole question is just one sheet of paper. Okay. Not those kind of whole book of things. It kind of sometimes scares students like, oh,
Do I alternate?
some are here. So I have, because they wanted to alternate the color, right? So yeah, you're gonna put the yellow
So
here.
we
and then-
do it one seat apart still. Can we fill this out?
I think so. I mean, if we can't, then we put, maybe we have like some like in between, and then maybe yeah, I think should be enough 120. But we can add on like maybe a few in between if we can't fit everyone. Like,
Okay.
actually, it's easier if I just put on all these. So I put all these, like the white one, and you kind of